My name is Eve Dirksen, and it is my pleasure to introduce to you our first speaker of today, who, as mentioned by Isabel, is Ruben Kranenburg. And Ruben obtained his master's degree in chemistry from the Free University in Amsterdam, where he specialized in the use of chromatography, mass spec, and capillary electrophoresis, so a very important fundamental. After working at Omegam and Waters, Ruben turned himself in with the Dutch police, and starting out as a forensic advisor and a chemical expert, Ruben concentrated on the quality aspects of analytical investigations, and not only by setting up quality management systems, but also by validating analytical methods. And in this way, Ruben was able to help get the police lab at Amsterdam certified for forensic investigations. And at this moment, Ruben is both a coordinator of the forensic lab in Amsterdam, as well as a PhD candidate in forensic analytical chemistry. And the project he is working on is a collaboration between the Van het Hof Institute of Molecular Sciences of the University of Amsterdam and the Amsterdam Forensic Lab of the Dutch Police. And today, Ruben will talk to us about the use of infrared ion spectroscopy and how this can help in identifying isomers of new psychoactive substances. Ruben, I'm looking forward to your presentation. The floor is yours.
So thank you for the very nice introduction, Eve. Well, I'm going to speak about infrared ion spectroscopy, which is an MS-based approach for reference-free NPS drug isomer identification. So, well, I can almost skip this. My name is Ruben Kranenburg. Well, being an analytical chemist, working at the police, the Amsterdam police, and besides that, a PhD student at the University of Amsterdam in the group of Professor Ion van Asten. So what I'm going to share with you, I'll start with well, the challenges we currently face in the forensic laboratory with the new psychoactive substances, a new type of synthetic drugs. Then continue with several analytical strategies we have in the lab, focusing on both well, known NPS, we already know what you're dealing with, or you have the reference standards, or totally unknown NPS, in which infrared ion spectroscopy proved to be a very helpful tool. Well, I'll tell you something about the technique, also some application on case samples, finish with some conclusions. But first, the challenges with the new psychoactive substances. Well, what is the challenge? Well, then it's good to look back at the forensic, the illicit drug market we have worldwide. And traditionally, like more than 10 years ago, the illicit drug market consisted of the common drugs, molecule substances like cocaine, heroin, ecstasy, which is MDMA. You can see the structures here. And what you can see is that those structures are very distinctive from each other. Large differences in molecular mass, chemical properties also, and we faced high concentration and relatively pure samples. Well, if you look at the last decades, that shifted a little bit. A lot of synthetic drugs entered the market, and also a lot of synthetic designer drugs with small modifications towards the common drugs. For example, if you look at the top row here, this is the amphetamine structure. There's only a small modification, which is that fluorine group attached to the ring. And as you can see, it's there are 3 possible isomers, and we can all see them in the forensic field. So the market has become a lot more complex with a lot of small modifications and isomeric forms. So why is this a problem? Well, if you look at the Dutch opium wet or narcotic legislation in Holland, it's based on a fixed list of substances, and only certain isomers are currently controlled substances. For example, the 4-FA, 4-fluoroamphetamine, until now is a controlled substance, and the other 2 isomers are not. So that really gives a risk for false positive identification if you encounter one of them, it seems to be the other one. So why not simply put all of those isomers on the list? Well, there's also a clear trend of innovation. There's a rat race going on the forensic market. And what we often see is that after a certain isomer or certain compound will get a controlled substance, it's listed on the opium bed. What you see is that other closely related forms might also appear on the market. It's not only a Dutch problem, it's really a global issue. You can see that the NPS, new psychoactive substances, reported globally, and also the total number, it's even approaching 1,000 until now from the last decade. So it's really a vast majority of different substances going on this market. So to understand what the challenge is, it's also good to know what the traditional way of drug identification, what the drug identification workflow is in the forensic laboratories. And this is what we do at several locations within the Dutch National Police, but also worldwide, the golden standard method for drug identification. Well, we start with an indicative colorimetric test, so the simple spot test. You might have seen it on television, gives the blue color with cocaine. And then we have a single quadrupole GCMS, and we do a full screen analysis. We also have some reference standards available, and then we apply identification criteria, because we only have to identify it, on retention time, and also the mass spectral match with your reference spectrum. If you take this this approach for the traditional drugs, the common drugs, so this is a mixture of the cocaine, the heroin, amphetamine, all those type of drugs, you can see that the chromatography is quite easy, they're pretty well resolved. And also the mass spectra are, there's large differences in both fragments and intensities. So if you apply that set of criteria, it's fairly possible to identify the substances. But that's shifted now for those closely related isomers. And for example, if you go back to our group of the fluorinated amphetamines, the ring positional isomers, what you can see is that both the chromatography, the separation, is much more challenging with some co-elution. But more importantly, also if you look at the mass spectra, they're pretty much the same. Same fragments, also the same fragment identities. So this really holds a risk for false positive identification, because if you remember, only this certain isomers are controlled substances. So then you violated the narcotic legislation. But if you possess these, then it's not, you're not violating the opium vet currently. So that will certainly fail. What we also do in the lab, a technique very capable of those type of ring specific variation is spectroscopy. For example, infrared spectroscopy. Well, you can also apply that. You can see that the infrared spectra are very different for the three ring isomers. And then if you took a K sample, for example, those white-colored ecstasy pills, pretty easy to see that it's a match with the 4 positional isomer of it. But what you can also see is this big hump in the middle. It's coming from tablet filler. So it's another compound already, also present in the tablet. It's microcrystalline cellulose. And if you took other samples like darker colored tablets or less potent tablets, well, that can totally obscure the signals for your active ingredient. So then also applying a certain threshold to match scores will certainly fail. So you need to do something else. So what can we do? I think first, we can break up a challenge into 2 pieces. Well, you can have the known unknown NPS, so you want to identify it, but you have a certain clue what you're dealing with. You've seen it before, you know that the isomers exist. Ideally, you also have the reference material available, or you have your spectra in your library. Well, then we typically use chromatography, GCMS, in combination with GC coupled to a spectroscopic detection, like FTR or VUV. But what you also might encounter is a known, a new substance you've never seen before. It's not in your spectral libraries. Well, then you might be thinking about techniques such as NMR or higher SMS or tandem MS. But there are some issues with this. The reference material is not available for all compounds. Also, the limits of detection for the spectroscopic techniques, the infrared detection, are rather high. And NMR, besides being quite expensive, also not really suitable for mixture analysis, which, as you can see, the ecstasy tablets, actual pills here, well, there's indeed some colorants and other substances might also be present. So you cannot straightforward put them in the NMR. And also, as I showed, the MS is not very suitable for ring isomers. So what we did in the lab, very briefly, we'll show you some approaches to give you some insight for those known NPS, which I also put some energy in for my PhD research. And for example, you can do the VUV, vacuum ultraviolet detection. It's a spectroscopy-based MS technique, so no MS. shortly switch back to the MS, but only 2 slides of this. Spectroscopy-based technique using a very interesting part of the UV area, 125 to 250 nanometers. And that's the part where typically also water and oxygen start to absorb, hence the name vacuum, because you can use it in vacuum. Well, if you combine that with GC, there's only helium coming out of your column, you can use that. And it's a very interesting part because also the sigma bonds start to absorb there. There's an example of another set of ring isomers is the catenones, the methylated catenones. This is 4 mmC. Methadone is a controlled substance. This is 3 mmC. There's been a lot in the news last couple of months, but until now it's not a controlled substance. And there's another isomer, the 2 mmC. You can see the GCMS EI mass spectra are pretty much the same in here. But the VOV spectra are very different. So this technique is very capable to help you identify which specific isomer you're dealing with, especially in combination with MS. Another strategy we can use in the lab is instead of the traditional EI ionization at 17 electron volts, you can go for low energy ionization. For example, you can use the 15 electron volt. And what you can see is that the mass spectra is much more information rich. Basically the same fragments, but the intensities are different. We can use that also to identify the specific isomer. Here we can see that fragments are the same, but there are major differences in intensity. So if you have an unknown, you can clearly see that in this case, we're dealing with the 4 positional isomer. So that's another approach we can use in the lab. Third approach is, well, beside these spectra, again, for the fluoroamphetamines, they look very much the same. Even if you zoom in on it, but there are some very little minor differences in there, but they seem to be very consistent. So what we also did is you can apply multivariate statistics, like principal component analysis on it. And you can clearly also see that there are 3 different groups for all the 3 isomers in here. So that's, well, some approaches we can use in our forensic lab to identify the certain form. Well, if you want to know more, we publish on it. But good to know is that, well, for all those approaches, we definitely need reference standards and reference spectra available. So we cannot use it in all cases if you encounter a new substance or a new isomer. So and then I come back to infrared ion spectroscopy. It seemed to be a very useful technique also for those type of samples and dealing for really unknowns. So what is it? I'll start with just a funny picture to visualize what it might be. Infrared ion spectroscopy. It's like shooting your molecules into pieces, and not simply shoot them into pieces, fragment them, but also select the color of the laser light where they absorb the most energy and thus fragment most easily. And you can vary it, and then you can do a sort of indirect infrared-like experiments on an MS-based platform. So fragmenting molecules with your laser, shoot them into pieces, but hit them at their weakest, find the optimal color of your laser light. Well, where can we do it? Well, there's one place in the Netherlands. It's called the Felix Institute, part of the Radboud University in Nijmegen. And they have a tunable infrared laser in the basement. And you can go there and book some beam time and do your experiments. So, well, I thought it might be very interesting to go there. So well, if you want to shoot your molecules, you need an army. So you have to team up. And we teamed up with those very clever guys from Nijmegen. So we went there, Ion and myself from the police, University of Amsterdam. Also decided to give the project a little bit more scientific name, call it wavelength-specific fragmentation for NPS ring isomer differentiation. We could do some experiments. So what is the technique? Infrared ion spectroscopy. You can see the system on the picture here. Well, first, what you need is an ion trap MS or an MS platform. You can see the instrument here. Basically, it's just a conventional ion trap mass spectrometer. There's something on top, and that's the tunable infrared laser coming from the basement of the Felix Institute. And that's entering the ion trap. So it's going directly into the ion trap. Then what you can do is you do your experiments, and you can do precursor selection. So you select a certain ion in your trap, and then you use your laser to fragment it. It's called infrared wave number specific photofragmentation. And then you can record your spectrum out of the fragment intensity. So you create fragments in your trap, you can scan them, you can plot the intensity, and then you can record an infrared spectrum. That is not like a traditional absorbance-based infrared spectrum. It's an indirect IR spectrum based on your fragment intensity, so an MS-based IR spectrum. So what you then get in this platform is MS-like sensitivity combined with infrared isomer selectivity. And what you can also do is, since those infrared absorption, you can do prediction, you can do theoretical calculation, you can calculate those spectrum by quantum mechanical predictions. So we went there with our standards, again, the fluorinated amphetamines, the 2, 3, and 4, and this is what we got. We selected the molecular ion in the trap, we varied the laser, we saw some fragments occur from the photo ionization, and we recorded the different wave numbers. And you can see clear differences for the 3 isomers. So that already shows you that you can really use this technique for the isomer differentiation. So what you can also do those theoretical calculations. So this is the computed spectra, the theoretical calculation of the fluoroamphetamine, a certain isomer, the 4 isomer in this case. You can really attribute all those peaks, all those IR peaks to certain vibrations. So then if you go back to our analyzed spectra, you can really into detail understand what is happening. For example, if you look in yellow here, you can see 2 peaks, and it's shared for all 3 isomers. So all 3 isomers have that same peak. And you can attribute that to a specific vibration, and that vibration is originating from the amine part of the molecule. And since all 3 isomers have that same, that's not where the variation is. All 3 isomers have that same amine part. Therefore, it's can clearly understand that that vibration is always present at the same position. So on the other hand, if you look at this peak number 3, here it's totally mixed with this one. Here it's coming out a little bit, and here it's coming out completely. That one can be attributed to this vibration. It's a ring-specific fragmentation. You can understand that that vibration it might be a little bit different because it's influenced by the position of the fluorine on the ring. Same is true for this other vibration, also a ring-specific vibration. And this one is shifting more throughout the spectrum. So it shows you that those computations can really help you understand your spectrum, the observed spectra. Then we decided to use it on an actual case sample. So we took a sample from our police laboratory, and this is the GCMS data we already had. So there are 3 peaks visible in it. It's a mixture. Well, this one, the third one, we are not really interested because, well, it makes a very clear mass spectra. It got a clear match both in retention time and mass spectra with caffeine. So there's caffeine present in it, but well, it's not a controlled substance, not really interesting. But those 2 are more interesting. Focusing on the first, we saw a match. We saw a match with the methylated catenone, so the MMC, but GCMS was not able to tell us which isomer it was. So we took this sample, so the mixture, so the sample, did the infusion experiments in the system, and selected this molecular ion for the methylated catenone. Fragmented with the laser, and these are the 3 fragments we saw occur, and then we plotted the intensity of the fragments at the various wave numbers. So again, in black you can see the spectra of the case sample of the selected peak, and in this case we were lucky because we also had the reference standards available. So we took the reference standards, you could also collect a spectra of that, and very clearly you can see that it's a match with the 3 MMC with this isomer and not with the other 2. So this one was identified as 3-methyl metcatenone. Then going back to this peak in the middle, that one was more challenging. Out of the MS, there was no match in our libraries. We got some, we saw from the isotopes that it was a chlorinated molecule, so it was a chlorinated catenone, but we were not sure if it was an ethylated one or a dimethylated catenone. So that basically left us over to 6 possible forms of it. But also here, the theoretical calculations helped us a lot. So to understand, there are 6 possible isomers which we investigated. And first, from left to right, we want to know if we're dealing with an ortho, a meta, or a para isomer. And then you can see that in all the computations, which are the plots in blue, there's one peak over here and also over here that is present, which is highly diagnostic for the para-positional isomers because it's absent in the meta and the ortho isomers. And it's also present in what we analyzed in black in the spectra. So that clearly pointed out that we were dealing with a para-positional isomer. So that left us with, well, are we dealing with either a secondary amine, the ethylated form, or the dimethylated form, the tertiary amine? Well, the difference, what you can see in the calculations, is this peak here. And that one is very interesting because you can attribute it to this vibration. And this vibration, as you can see, that there's two hydrogens involved, and it's also a part of the amine part of the molecule. And that vibration is only possible if there are two hydrogens on the amine part. So if it's a secondary amine, and it's not possible if there's if it's a dimethylated form, because then there's only one hydrogen left. And since that peak is also absent here, this component was identified as 4-chloro-dimetcatinone. So very happy because, well, this technique helped us to identify the substances in our sample. But then I can hear you think already, well, you should only do infusion experiments. There's no chromatography involved up front. So what about if you encounter mixtures of isomers? If you get a mixture of 4Fa and 3Fa and 4Fa, because they have the same fragments, the same ions. Is there something possible? Well, it was a very interesting research question. We also decided to put some energy into that. And also, well, unfortunately, those samples do also exist in the forensic field. Mass attributed to fluorinated methamphetamine. Well, we didn't know what the ring position on the ring positional isomer was, and well, if you remember, it might be possible that if you violate the law, it's dependent on which positional isomer you're dealing with. So also for this, infrared ion spectroscopy helped us a lot. But first, if you selected the molecular ion and took the spectra, well, you came back with something like this, and that's clearly a mixed spectrum. You got already, if you look more closely, you can get some clues that because of this peak, it's also this is possible. But there might be some 2 isomer present in it. Also, the 3 might not be present, and the 4 might also be present. But this is not, well, clearly not identification. So we really decided to investigate more, to look a bit deeper into it. We performed some experiments called depletion experiments. So basically what you do there is you select a peak, a certain color of infrared light, for example, the 755 wave numbers, number 1, and then you give a large number of laser pulses. So basically you burn away all fragments originating from isomers that absorb at that specific wave number. And what we noticed is that the intensity starts to drop, and then at a certain level, it doesn't drop anymore, and it's stable. So that can show us that well, there's a mixture present, and that well, one of those isomers present in the mixture absorbs the light, fragments, breaks into pieces, and is gone, and the other doesn't absorb the light, cannot absorb that specific wave number, and stays in the trap. So the intensity is reaching a constant. On the other hand, if you look at the number 7, that's total depletion. So that gives you an indication that well, all isomers possible, if available in the trap, they all absorb at that wave number. And you can also already see here from the reference spectra, that's also the case. That is the case. And what you can also do is that you select well, a certain you selected a certain wave number, a certain color of infrared light, 1260 in this case. Then you give a lot of laser pulses, and basically what you do is you burn away one isomer. So all the molecules from this isomer will absorb the light, will fragment, and will and there leaves the trap, because you only trap the molecular ion. And then what's left over in the trap, all is left from a single isomer. So you burn away one isomer. Then you can do again your original infrared ion spectroscopy experiment. So in the second dimension, do it again, scan out your trap, by varying the infrared light. And then we obtain the spectrum like this. Okay? You can basically what you do is infrared to the power of 2 and MS to the power of 3. So you get this this spectrum, which clearly matches with the reference spectra, which you can see in red. So that's very nice. And then on the other hand, you can also subtract this spectrum from the original one and see what is left over from the signal. And that clearly matches with the 4-positional isomer, so the other isomer we also had. So this technique really helped us also to identify the mixtures, the mixture of 2 isomers in one sample. So that already brings me to the conclusion of my talks. What I showed you is that the infrared ion spectroscopy, it combines the benefits of both mass spectrometry and infrared, because it gives you the sensitivity, MS sensitivity, in combination with the infrared selectivity, mostly for isomers, ring isomers, and of course also the MS selectivity, because you can still do the mass selection in your ion trap. Well, I also showed you that the ring isomeric NPS identification in case samples is feasible, even if there are isomers. And also that the theoretical spectra, infrared spectra, really helped us for structural elucidation. But also here, if you want to know more, we published it in 2 papers in analytical chemistry. Very happy with it. You can see the links here in the slides. So that concludes my talk. But not before I can have to thank a lot of people involved, but most importantly in this study are the guys from the Felix Institute in Nijmegen that really helped operating the instrumentation, the laser, and do all the data analysis here. Fred van Genen, Gilbert, Jos Omens, and Jonathan Martens. So, thank you for your attention.